Okay. The only thing that we will not be covering in depth is the volume. That's the last section. I'm just gonna give you the basics with volume. I'll get into a little bit more with juniors, but for you guys, you will get all of calculus, all of what you need to have for calc. So here we have, we're continuing with integrals, applications of integrals, okay? First is integral is a net change, and if you didn't get chapter 6, so that's where I was saying the juniors, you should be fine for this. This is an all calculator okay chapter. In other words, all I'm really going to look for on the quiz is the setup of the integral, and then you plug everything into your calculator. So if you have your calculators handy, you'll be using them. Okay, well, we'll get there. Okay. So integral. In integrals, these are viewed as a net change over time. Okay. We did this in the very beginning of chapter 5 where we had a train that was moving and we said, oh, it's going 75 miles per hour for 2 hours. So we looked at the area under the curve. Now, some of this is a little bit of review. So let me just go through this particle motion. So when velocity is positive, we know it's moving to the right. If velocity is negative, it's going to be moving to the left. Did we talk about displacement? We talked a little bit about displacement.
In physics, we know what displacement
Okay, so displacement is what?
is. It's the distance from start to finish.
Okay, now, what if you don't know the position function? What if you know velocity? So remember, velocity is the derivative of position. So if we work backwards, in other words,
The antiderivative.
we could do the antiderivative. So displacement. Okay. So if we do the antiderivative of velocity from A to B, we will end up with the position, right? Right? So basically what this gives us is your position at B minus your position at A. Usually S or X is the position function that we use. So final position. Final position is going to be the initial position plus displacement. So it's basically where we start plus how much have we traveled. Remember, if we go backwards, that counts as like a negative, forward positive. Total distance. Total distance is the absolute value of velocity. Okay, remember, it's kind of like if you start from school or start from home and you go to school and then you go back home, your displacement would be 0. However, the total distance traveled would be double the distance from home to school. All right, let's look at an example. So we have a function. We have velocity. Okay, it's moving. V of t is the velocity in meters per second of a particle moving along the x-axis. So we're going to, A, determine when the particle is moving right, left, and stopped. Okay, so the first one has no calculus involved. What did I highlight, the very first thing? When V of t is greater than? Okay, so I basically want to set this equal to 0 and solve for t. So I get t equals 8. This is part A. So I'm going to draw, now notice this is my number line goes from 0 to 10, with 8 being a place where what? What happens at 8? Okay, so, but 8, specifically at 8, that's where the particle is stopped. Because remember, we set the velocity equal to 0 here. So let's pick a test number between 0 and 8. Whatever. 6. Plug 6 in. Do we get positive or negative here? Positive. And then pick a number between 8 and 9, or 8 and 10, say 9. And we get negative. So where is it moving to the right? Good. And it's moving to the left from 8 to 10. And it stopped at t equals 8. you know what, if you use parentheses, it's okay. Because it's the same as increasing and decreasing functions. It just is. Parentheses are okay, brackets are okay for here. All right, B. Find the particle's displacement. So above there we said displacement was the integral from 0 to 10 of v of t dt. Right? This is displacement. Over the given time interval, right here, from 0 to 10. Now, just to save time, okay, I know that you can integrate this. This would be 24t minus 3t squared over 2, and then you would plug in 10. This is the part where it's fine with me. As long as you show me the setup, you can go right to plugging this into math 9. So if I go to math and then 9, we have from 0 to 10. And then we have 24 minus 3x and dx. So just plug it in. That's fine with me. We get 90. You put in the function, then you put a comma x, comma 0, comma 10. So we get 90 here. What does that mean? 90. Okay, so the displacement means I have ended up 90 meters to the right of where I started. What can I plug in? That's what I just did. Right. You have to integrate it first.
Oh, that's why.
Okay, so now my final position is equal to my initial position plus my displacement. Now, this here, S of 0, this is my initial position. Because remember, 0, what I have here, this is time. So I'm saying the position when time is 0 is equal to 3. So I have 3 plus my displacement, which was 90. So 3 plus 90, we get 93. And that's meters. So I'm ending up at a position of 93 meters. Question on that? I'm just, that box at the front, the very, okay, that I put a, previous years I kind of put a star here, but we highlighted everything. Just know all of those really well. That's going to help you a lot on the homework assignment if you just refer back to that table for that part. Okay, so last one is find the total distance traveled. The box that has all the information about position, displacement. So how do we know total distance traveled? What was that? If we look in the box, it was the absolute value of velocity integrated. So we went from 0 to 10 of absolute value of 24 minus 3t dt. You could, again, break this up and do this by hand, but, oh, actually, you know what? What would be easy here? Do you remember how I said you can, maybe you can't change it. I was going to say you could go back and make this an absolute value, but now that I'm thinking about it, it might be just easier just to type over. So 0 to 10. And then we want, what's that? It's still 0 to 10. No? Because remember, it went backwards from 8 to 10, and we want to count that as positive. Did everyone understand why we have to do the absolute value? What do we get?
102.
About 102.
How do you do it on the DDP again?
You do. It's still math 9. You do absolute value. Good? All right, let's try the next one.
So all the integrating and doing the
Everything gets done on your calculator here. I mean, if you want, you can practice it, but
You don't need to.
I'm more concerned about, can you set up the problem correctly? And then you could do the rest on your calculator. All right, this is exactly the same as the last one, just here's my velocity is now sine. So how do we know when velocity, so I want to set this equal to 0. When is sine equal to 0? Between 0 and 2 pi. Think about the unit circle. When is my y coordinate 0 and pi? Okay, so on my number line, I have 0, pi, and 2 pi. Again, this is my velocity function, so I haven't done any antiderivatives or anything. I started with velocity, we set it equal to 0, so basically we know it stopped at 0 and pi, but we want to see what's going on in between these values. So pick a number between, say, pi over 2. What's sine of pi over 2?
Sine of pi over 2 is
1.
Oh,
1. It's 1. It's positive. Okay. It's all right. It's all right. It's, it's been a while.
3 pi.
How about something between pi and 2 pi? Say, it's negative. All right. So, where is it going to the right? Where is it moving to the left? And where is it stopped? Be careful here at, there are 2 points, right? 0 and pi. Are we good with part A? It's just like the last one, but instead of a linear function, we had a trig function. So the order is set it equal to 0, make a little number line, figure out where it's positive and negative. Question?
Why is it?
What were you? Oh, you know what? It is.
I was gonna ask why is it stopped at N? Why is it stopped at 2 points?
This sign is 0 there also.
Okay,
Sorry. It's actually stopped at 0, at pi, and at 2 pi because its sign is equal to 0 at all 3 points. Do you have a question, Carmel?
Can you just reiterate how you find the stuff at point?
It's just where you got
Where-
here,
where the-
where it's equal to 0. It stopped. Where do we know it's...
Oh, like where the velocity, okay, because we set the velocity to 0, right?
Yeah,
That's where the velocity is.
right.
Okay, makes sense.
Okay, for B, how do we find displacement again? Okay, so what was the formula? It was the integral from 0 to 2 pi. Now, plug that into your calculator, or maybe you can think about this intuitively. Here, guys, just think about the sine curve. What happens when you go from 0 to 2 pi? The region above and below are going to end up canceling each other. So it's 0. Plug it into your calculator, you'll still get 0. Yeah, and when you plug it in, you'll still get 0. Okay, final position. Oh, and this was, sorry, this was also meters. Final position, so S of 0 equals 1, that's my initial. So it's the initial position plus displacement. So I end up at a position of 1 meter. And then finally, for total distance. Now, because the part that goes below counts as positive now. So from 0 to 2 pi. Should get 4. So if I plug this in, so I have from 0 to 2 pi, and then we have absolute value.
Wait, displacement?
I got 4.
For the displacement, I didn't get zero.
Did you put absolute value in by accident?
No. For the displacement, I got 0.3.
Oops, I didn't mean to do that one. No, it should be, did you put your calculator in degrees or radians? Check radians. Ben.
Oh, yeah.
Okay, so total distance traveled is 4 meters. Questions?
Because you just plugged it in?
That I did. Just into the calculator.
Wait, what did you plug in?
Exactly what you see.
Oh. Oh, with the absolute value, got it.
That's what it looks like. All right, next one gets a little more complicated. So a car is moving at an initial velocity of 5 miles per hour. So here's my initial velocity. And it accelerates at 2.4 t, miles per hour per second. Remember, acceleration is like per unit of time per unit of time.
0 to 8?
So how fast is the car going when the 8 seconds are up? So A, we want to find the velocity after 8 seconds. This is kind of like, instead of, remember how I said final position? We're looking for final velocity. So we're looking for initial velocity plus change in velocity. Does that make sense? Like it's starting out with an initial velocity of 5 miles per hour, and then over the 8 seconds, it's accelerating. So it's going to be what? It's going to be 5 plus. How do I find the change? So if you remember what I said in the very first page I highlighted, it's a net change over time. So that change can be in anything. It could be in velocity, it could be a change in acceleration. This one is going to be the integral from 0 to 8 of velocity. What's our velocity? Or I'm sorry, acceleration. That's what I meant. I should say net change. So plug this in. So I have 5 plus, and then we go math 9 from 0 to 8. We put 2.4x dx. And we get 81.8.
I do get 24.
It's 2.4. Yeah. You just get the constant plus, or constant times the variable. So if it's like the integral of 4 dx, it would be 4x.
No, on a given point, so like,
It'd be a
here's
It's just a rectangular region then.
so it'd be 4 times
The interval. B minus a. Okay. How far did the car travel during those 8 seconds? So we have to find total distance. How do we find the total distance? It's going to be the absolute value of velocity. But we don't have velocity, we just have acceleration. So we have to... Okay, so this one, we actually do have to do a little bit of integration, but it works out easily. So, what's the antiderivative for 2.4t? It's going to be 2.4t squared over 2, which ends up being 1.2 t squared plus c. Now, I have And by the way, we could have solved this by finding the velocity function also.
But here I have v of 0 equals 5, so I could plug that in.
So I get c is equal to 5. So my velocity is 1.2 t squared plus 5. Are you okay with that so far? This is exactly, so this would be a little piece that you guys missed, I think.
It makes sense, it's just.
Yeah, it's basically, it's plus c, and you have to use a particular point and plug it in to figure out what c is. And then you have your actual function.
This probably sounds.
Yeah.
Wait, but why aren't you having the
Okay, so now I'm going to do the total distance. So I went from 0 to 8 of the absolute value of that result. So basically take that. Remember, we're starting with acceleration. So we work backwards 1, so we get velocity.
Why are you putting 0 instead of
Because v of 0 equals 5. It's like working, does it make sense? It's kind of, it's just, what do we get for that, guys? Anybody get it?
81.8 is the one.
It is. It's my final velocity.
Why would we use after the velocity?
Is that meters per second? No, that's so for final anything, it's always the absolute value.
No,
For final distance.
total distance, yeah. Okay,
The next meter?
a few more examples.
Miles, not, is that miles?
Oh, was that meters?
No, it's miles. So I don't know.
It was
How
in-
far do you stop? How far
Use it, Miles.
No, the car would not travel that far in 3 seconds.
Hold on. No, it's not miles.
That wouldn't happen.
Oh, you know what, guys? Hold on. Hold on. So, let me just go back here. This was miles per hour per second. So when we work backwards, what do we get for velocity? Basically, every time when we integrate it with respect to seconds. So it basically takes away the per second, and we're just left with miles per hour. We're okay with that? Now, when I integrate it again, this was again in seconds, but it was miles per hour. So we actually have to take this 244.8 and think about how many seconds are in an hour. So we're going to divide that by 3,600. And what do we get?
0.068.
No, that's how many miles it is.
And that's how many miles. And then if you wanted, you could change that into feet if you wanted by multiplying. Okay? Yeah, you're not, in 8 seconds, you're not going to go with that.
Well, depending on
True. Okay, total consumption over time. So again, the integral is a way to figure out a net change. Okay, an accumulation. So to find the cumulative effect on a varying rate of change, just integrate it. Okay, so from 1970 to 1980, the rate of potato consumption in a particular country was given by this. Okay? So with T being years since the beginning of 1970, how many bushels were consumed? I don't know, look that up. Were consumed from the beginning of 1972 to the end of 1973.
So would that be 2 years or?
Yeah, so if we're going from 72 to 73, and it started counting, so the whole point to this one is just making sure you have the correct amount, right, Josh? Yes. So if I'm starting in 1970, But I only wanna look at the accumulation from 1972 to 73. Oh, and actually be careful. This is beginning of 1972, so that's 2 years after 1970.
You have to go from 70 to 72 first, though. So you have to.
No. It's just looking at the beginning of 72 to the end of 73. That's really a total of 2 years. So consider the end of 1973 would correspond to the beginning of 1974.
So you could technically have 1972 on the bottom.
Why is it
Because this says beginning, we want to have this being the beginning. Just, in other words, when they're looking at December 31st versus January 1st, it's going to end up, this is the better approximation. So we look at how many years past 1970. And then we just put this in our calculators. It's just a calculator problem. And this is millions. It's just whatever the net bushel. All right? That's all you do for that. Okay, I think we have just 2 more examples, and then I have a worksheet for your assignment. Also, you know that tomorrow is switched to Thursday, so tomorrow's bonus. Thursday's meeting, so I'll be here for bonus tomorrow. Who said they're coming in for review? Okay. Okay, so example 5.
I'm observing because when I write down stuff, it doesn't process, so I'm doing a screencast, I'm trying to, I'm gonna watch it, pay attention, and then
I like this process. Okay, example 5. This is velocity here, just so you know. The graph of velocity is given. Where is the particle at the end of the trip? What does that mean? That's talking about final position. How do we know final position? What did we say that was? That was the initial plus displacement. Now I don't have a function. I have the initial position. It says when t equals 2, x is 2. T equals 0, x equals 2. Plus the displacement. Now I don't have a function to integrate, but I can figure out the actual area under the curve. So take a look. I have a trapezoidal region and then a triangular region. So can we figure out the area of these? 2 plus. What's this area? It's 1/2 times the height and then base 1 plus base 2. So we get 9. And then what about this one? This is 1/2, the base is 4, the height is 2. And what do we have to do with that? We have to actually subtract it, because when we talk about displacement, right, anytime it goes below the x-axis, we count that as a negative, because it's going in the reverse direction. Okay? Yeah, I hope we can handle the rest. 2 plus 9 minus 4. 7? You're starting to guess yourself there? Second guess? All right, how about B? What's the total distance traveled? Now, does the initial position matter? No. All we care about is the area under the curve, but we want to just make sure that they're all positive. So basically this one was above, so that's going to be 9. And then instead of subtracting the 4, we just want to make it a +4. We've done some of this before, so it shouldn't look that different. We've done some where we've done like total distance or total area under the curve. Okay with that?
Wait, why did we add as much traffic?
Because this is a negative velocity, but it's still traveling here. So when it goes below the, remember, what's total distance traveled? It's the absolute value. Oops. It's the integral of the absolute value. So imagine if we took this and we drew the absolute value of it and then found the integral. It would be as if you like flip this up here and then everything would end up being positive because it's above the x-axis.
We only do that when we're doing velocity.
Right. Okay, last one. This one we're going to use trapezoidal rule. Okay, so a pump connected to a generator operates at a varying rate, depending on how much power is being drawn from the generator to operate other machinery. So this is the rate in gallons per minute at which the pump operates. It's recorded at 10-minute intervals for an hour. Okay, so we're going to use trapezoidal approximation. So this is nothing new.
0 plus.
Okay, what is the height? The height is 10, so it's going to be 10 over 2. And then 58 is used once. 2 times 65. Yep. That's fine. You can write it that way. And then the 63 is used once. So we end up with, I don't know. Double check, but there isn't. So for 2 of the sections, I liked the worksheets that I had better than the first work. So this is the homework. How you do that here? Stop internally laughing at me. I know you are. Let me pause it.